Number one says, given the information in the diagram, which pair of triangles cannot be proven congruent? So if we take a look at answer choice number one, we were given that AC is congruent to CD, and we're given that angle BCD is a right angle. So that means the angle BCA also has to be a right angle, because if two angles are supplementary and one of them is 90 degrees, then the other one has to be 90 degrees to make 180. Notice how both of these triangles share side BC. So when we have a shared side between the two triangles, we can say it's congruent to itself by the reflexive property. So BC is congruent to itself. So we have side, angle, side. So that makes the two pairs of triangles in number one congruent to each other by SAS. In answer choice number two, we are given these two angles and this pair of sides, and we also have the congruent vertical angles, because remember, vertical angles are always congruent. So we do have AAS. So these two triangles are congruent. That is AAS. Over here, we have two pairs of sides already, and then we have a shared side congruent to itself by reflexive. So we do have side, side, side. So that leaves us with the last two pairs of triangle, the last pair of triangles here. We do have two pairs of sides in an angle, but the angle isn't between the two sides, so it's not SAS. What this would be is ASS, which is a bad word that you shouldn't be putting down on your geometry regents review packet. Or if you read it backwards, SSA, which is the same thing. Because if you read it backwards, it's the word you don't want to be writing down here. So these are not congruent. That's the answer choice we're looking for. In number two, we're told that we have a quadrilateral and that DE is the perpendicular bisector of AB. The perpendicular part means that it forms 90-degree angles where it intersects AB. So we have a bunch of 90-degree angles here. The bisector part means that when it bisects AB, it splits AB in half. DE is the bisector, AB is getting bisected. So AB is being split into two equal parts. And now it's asking us which statement is always true. The first one says that angle ADC, that's this one over here, is congruent to angle BDC, that's this one over here. Well, in order for this to be true, these two triangles, triangle ADC and triangle DCB, would have to be congruent. And I'll highlight those two triangles so you can see them. These two triangles do share a side in common. So we do have side, angle, side. So these two triangles are congruent. So since the triangles are congruent, CPCTC tells us that the corresponding angles will also be congruent. So this statement is always true. But we can take a look at the other ones to see why the other ones might not be true. And I'm going to circle it. Number two says angle EAC, that's this one over here, is congruent to angle DAC, that's this one over here. In order for this to be true, these two triangles would need to be congruent to each other. So that's this triangle over here and this triangle over here. But even though we do have this shared side over here, all we have is an A and an S. We would need another S or another A to prove the triangle's congruent. So we don't know the triangles are congruent. We don't have enough information, so we can't CPCTC these two angles. The next one says AD is congruent to BE. So that would require these two triangles being congruent to each other. But the only thing we know between these two triangles are these congruent angles here, which are right angles, and they also happen to be vertical angles. Oh, we also know the side over here. Yes, we do. But we don't have the other side. And we don't have another angle. So just like with answer choice 2, all we have here with these two triangles is one S and one A. So we don't have enough information to say the triangles are congruent. So we don't have enough information to CPCTC AD and BE. The last answer choice says that AE is congruent to AD. So that would require this triangle and this triangle. And it's the same as with the other one. We actually looked at these two triangles before for answer choice 2. They share the side in common. They have the right angles, but that's all they have. All they have is one S and one A. SA is not a way of proving the triangle's congruent. We would need something else in order to know that they're congruent to CPCTC, AE, and AD. Okay, moving on to number 3. Here we're writing a proof. So over here, what we're told is that AE is parallel to DF. And we're told that EB is parallel to FC. Lots of parallel lines going on here. And we're told that AC is congruent to DB. So AC is from here to here, and DB is from here to here. So the first thing I'm noticing, and I'll come back to the parallel lines in a second, the first thing I'm noticing is how this line segment AC extends further than the side of the triangle. The side of the triangle is AB, but this is too much. I want AB. And over here, we're given DB, but that extends further than the side of the triangle. The side of the triangle is DC. So that's too much. I just want DC. I want the side of the triangle. So that tells me that I'm going to have to make it smaller here. And when we make something smaller, that's subtraction. So when I start writing the proof, and I'm going to start writing the proof now, that's actually the first thing I'm going to do. I'm going to subtract so that I could get AB congruent to CD. And that way I can at least have a side to work with. And then we can figure out the rest. And I know I didn't finish marking everything in the diagram and drawing conclusions from the parallel lines, but I want to go with the subtraction first. And also, just so we keep our goal in mind, our goal is to prove the two triangles congruent. So getting AB congruent to CD would definitely help us with that because that would get us a side towards what we need. So I'm not going to write all the givens just because I don't have that much space over here. But on the test or on the Regents exam, you definitely do need to write the givens. Otherwise, they will take points off for that because all of your conclusions are based on the givens. So I'm only going to write down the one given that's relevant to what I'm doing right this second. But once again, you need to write down all the givens. Okay, AC congruent to DB. So I want to end up with AB. So if I take AC and I subtract BC from it, if I take this whole thing and I subtract this, then I'll be left over with AB. Let me mark that a bit nicer. AB. So I want to subtract off BC. And that's going to leave me over with AB. Oops. Keep switching me off the marker. On the other side, I'm starting with DB. And I want to be left over with CD. So I'm going to take DB and I'm going to subtract away this part. So I'm left over with CD. This part also happens to be BC. So here's my subtraction. But the thing is, in order to do subtraction, I have to be starting with congruent and subtracting congruent in order to get congruent. But notice how, yes, AC and DB, the two starting segments, were congruent from the givens, but they never said that BC was congruent to BC. We need to say that in our proof before we can subtract it, because remember, we have to start with congruent and subtract congruent. So I actually have to add a step in that says BC is congruent to itself by the reflexive property. So I'm going to pause the video so I can move these down so I don't have to waste too much time on the video, because I'm going to add in a step in between 1 and 2 saying BC is congruent to itself. Okay. So I'm going to add in that BC is congruent to itself, and that is by reflexive property. And then I can do my subtraction, and that is due to the subtraction postulate of congruence, but you can just write subtraction for short, and everyone knows what you're talking about. And that makes this step 4, and that is substitution. And the reason that's substitution is because we're saying this minus this is this. AC take away BC is AB, and this minus this is this. DB take away BC is CD. And now we have a pair of sides that we need. Now let's try to find either more pairs of congruent sides or congruent angles. Since we had parallel lines in our givens, I'm thinking that we're going to be finding some congruent angles here somewhere. So let me highlight some of my parallel lines. So these two are parallel to each other. And I'm always looking for a transversal when I have parallel lines, because parallel lines cut by a transversal give us a lot of good angle relationships that we can use. And notice here how we have alternate interior angles. And alternate interior angles are congruent when lines are parallel. So since I knew from my givens that these lines were parallel, I can definitely conclude that angle EAB is congruent to angle FDC, and that is because alternate interior angles, I'm abbreviating due to lack of space, but please write out the full word. This is not a real abbreviation. Alternate interior angles are congruent when parallel lines are cut by a transversal. So now we have an S and an A. And remember, we have another set of parallel lines from the givens. So this is getting a little bit messy, but I want to highlight my other pair of parallel lines. I'm going to highlight them in blue. And once again, this is getting a bit messy. And here's the transversal that intersects them. And let's think about what the relationship is between these two angles. And it might help to think of it turned a little bit, but these are the two parallel lines. This angle is above and this angle is below. They are on different sides of the transversal and both outside of the lines. So those are alternate exterior angles. And I'm going to draw it on the side for you turned up a little bit better. So here are the two parallel lines and the transversal in between. And then this one is located like on the bottom. So let me draw this picture better. So I drew my picture a little bit better. And these are the two parallel lines right here. And this angle is kind of located over here, and this angle is kind of located over here. So they're both outside of the parallel lines. They're both, this one's on the bottom, this one's on the top. They're both outside of the parallel lines on different sides of the transversal. So those are alternate exterior angles here. So let me get a little bit more space here. And then I can say that angle EBA is congruent to angle DCF because alternate exterior angles, once again, this is not a real abbreviation, are congruent when parallel lines are cut by a transversal. And alternate exterior angles don't often come up. It's usually alternate interior angles or corresponding angles. And now we have all the information that we need to say that the two triangles are congruent to each other. The two triangles are congruent to each other by ASA because we have two congruent pairs of angles with a congruent side in between. Moving on to number 4, we have two triangles, Joe and Sam, and we're looking for which mapping would not lead to them being congruent. So I'm going to draw my two triangles, Joe, and just because I went like this, I have to go like this for Sam. And angle E is congruent to angle M, and EJ is congruent to MS. So already we have an A and an S. So we're looking for which one does not make them congruent. So let's try out the answer choices. J congruent to S, that does, that's ASA. O congruent to A, that does, that's AAS. EO congruent to MA, that does, that's SAS. And finally, JO congruent to SA, well, that's ASS or SSA, which is the same thing as ASS if you read it the other way. So this one does not make them congruent. Moving on to number 5. Number 5 says that in the two triangles below, DB is congruent to BE. And it asks which triangle is needed to prove triangle ABE, that's this one, congruent to triangle CBD, that's this one, using side angle side. So what we should do when we have overlapping triangles is we should redraw them separately. So here's my yellow one. Here's my red one. The red one is DBC. And the yellow one is ABE. And we were already given that DB is congruent to BE. Sorry, I couldn't read my own handwriting. This triangle is ABE. That's an ABE. So we're already given that DB is congruent to BE. So we're already given that these two pairs, that this pair of sides is congruent. So we already have an S. Now the triangles are overlapping, so there's going to be something shared between them. So I'm going to look for a shared angle. And I do see that there's a B here and a B here. So they do share angle B. So angle B is congruent to itself by the reflexive property. Now for SAS, I would need AB over here to give us the second side, and I would need BC over here. But that's not an answer choice. Alternatively, I do notice that we have this piece of DB. And if we had this piece, if we had AD, then we can put it together and we could make AB and get this. And over here, we already have BE. If we had this little piece EC, then we could put this together and we could get BC, which would make SAS. And that's here. These two little pieces that we would need to add together to get the whole big things are there. It would have been more straightforward if they just had AB congruent to DB there, but these pieces are the same thing because we already had these congruent, so we could add them together. We're not looking for angle 1 or for number 1 or number 2 because those mention angles, and we already had the angle that we need from the shared angle, so we didn't need that for SAS. That would have given us something else, maybe like AAS or ASA, but we needed SAS. And then AE congruent to CD, that didn't give us the sides that we needed. We needed the ones that were directly next to the congruent pair of angles, because remember, we need the angle to be included between the two congruent sides, SAS, SAS. In number 6, we're writing another proof. And this time, we still need to prove that two triangles are congruent, but our givens are that a different pair of triangles are congruent. So we're given that triangle ABE is congruent to triangle CBD. So we're already given that the big triangles are congruent. And our goal is to prove that the smaller triangles are congruent. So what we're going to do is we're going to try to use the fact that the big triangles are congruent to CPCTC more information that's in the small triangles as well. So what we're going to do is we're going to try to find parts of the big triangles that are also part of the small triangles. So let's take a look and let's see. So first of all, between the two small triangles, I do see that we have vertical angles. Yes, just wanted to make sure. Let me put my markings back. We do have vertical angles. Remember, vertical angles are always congruent, so that gives us a pair of angles already to prove the two smaller triangles congruent. Now, remember that the two big triangles are already congruent. What jumps out to me is that angle A over here is part of the big yellow triangle, but it's also an angle of the small triangle. And if I take a look at the names, A corresponds to C. And look at that, C is part of the big triangle, and at the same time, it's also part of the small triangle we need to prove congruent. Since angle A and angle C are parts of the big triangle, we can CPCTC them because we already know that the big triangles are congruent. And remember, if triangles are congruent, then all the other corresponding stuff about them, sides and angles, are also congruent. I don't know if this is going to be helpful right now, but I could very well say that angle A is congruent to angle C by CPCTC. Now I need a side. Since I need a side, let's see what sides of the big triangle I can CPCTC. But first, even though I don't have my complete plan yet, I am going to start writing up the proof so that way we don't lose track of the reasons for why we're doing things. So we were given that triangle ABE, the big yellow triangle, was congruent to triangle CBD, the big red triangle. And then we concluded that in the small triangles, we had angle AED congruent to angle, oh, that's not an E, that's an F. That's AFD. Let me change that. Angle CFE. And that's because intersecting lines form congruent vertical angles. Once again, this is not a valid abbreviation for vertical angles. Please write it out. And then we said angle A is congruent to angle C due to CPCTC because they are corresponding angles of the big triangles that we already knew were congruent. And they're helpful to us because not only are they angles of the big triangles, but they're also angles of the small triangles. So by CPCTCing it from the big triangles, since we know that the big triangles are congruent, it's also giving us more information about the small triangles. Now we said we need a side, because right now we have an A and another A. We have AA. That's for similarity. That's not for congruence. So we need to get a side. So I'm going to take a look at the triangles that we already know are congruent and see which sides I can draw conclusions about. So AB is congruent to CB because those match up. Where's AB? Here's AB and here's CB. And BE is congruent to BD. Do the CPCTC. This is all do the CPCTC because we already know these two triangles are congruent. So B is right here and BD is right here. Ooh, I have big piece, smaller piece, and it would be helpful if I could get this. So if I have the big and the piece, if I take the whole and take this away, I can be left over with this. So that's subtraction. We're going to take this, subtract away this, and get this. Same thing here. I have this. If I subtract away this, I could get this. And then I'll have AAS, and that works. That will prove my two small triangles congruent. So let me write this all down so far. So we have AB is congruent to BC, and that was due to CPCTC because they are corresponding sides of the two big triangles that we already know are congruent. And then we had DB congruent to BE, and that's also due to CPCTC because they're corresponding sides of the big triangle that we already know is congruent. And now we said we're going to subtract to get AD and EC. So let's do it. Let's figure out what we're going to be subtracting. So here I'm going to be taking AB, that's my big long segment, and I'm going to get rid of DB from it because I want to be left over with AD, which is the side of the small triangle. And over here, I'm starting with BC. And from BC, I want to take away BE because I want to be left over with EC, which is a side of the small triangle, and I'm interested in the small triangles. So this is subtraction. And this is substitution because this take away this is this minus this is that, and this take away this is this minus this is that. So we're substituting for what's equivalent, what the subtraction actually leaves us over with. And now from here, we can end the proof, and we can say the two smaller triangles, AFD and CFE, are congruent, and that is due to angle, angle, side, angle, angle, side, angle, angle, side. And we are done with this proof. In this question over here, we have a rhombus, and we know that PR is 16. So that means each of these is 8 because diagonals bisect each other because a rhombus is a parallelogram. And QS is 30. So that means that each piece over here is 15 because once again, diagonals bisect each other because a rhombus is a parallelogram. Also, remember that diagonals of a rhombus are perpendicular. So these are all right angles here. So what we have are right triangles. So what we can do is we can do Pythagorean theorem with any of the right triangles to find one of the sides. 8 squared plus 15 squared equals to c squared. 64 plus 225 equals to c squared. 289 is equal to c squared. So c is equal to 17. And since we're looking for the perimeter, all four sides of a rhombus are equal measures. So we're just going to do 17 times 4, and that's going to give us the perimeter. And that is 68. Over here we have a rectangle, and we need to find the perimeter of the rectangle to the nearest tenth. So we have two ways that we can go about this. The angles of a rectangle are right angles. So here we have a 30, 60, 90 triangle. And remember, the ratio of the sides of a 30, 60, 90 triangle are 1 to radical 3 to 2. What we have here is the biggest side because it's across from the largest angle in the 30, 60, 90 triangle. So we have the 12 part. We have the 2 part, I mean. So the smallest would be 6. It would be half of that. That's across from the 30-degree angle. And then the middle biggest angle would be the smallest times radical 3. So that would be 6 radical 3 for the middle biggest side across from the middle biggest angle. And then you can put into your calculator 6 plus 6 is opposite sides are congruent, plus 6 radical 3 plus 6 radical 3. You can hit enter and you can see what it is. Another option that you have in order to do this is, since it does say to round and it doesn't ask for an exact value, you could use a trig ratio because you do have a right triangle here. So if you decided to use a trig ratio, since you already had the 12, you might have chosen to use either sine, opposite over hypotenuse, or cosine, adjacent over hypotenuse. I'll set up cosine of the 30-degree angle equals to x over 12. And then if you were to solve your cosine ratio, that would give you this side over here. And then you can either set up another trig ratio or use the Pythagorean theorem to get this other side. Regardless of how you do it, you should get the same answer either way. And you should get 32.8 rounded to the nearest tenth.